All right. My name is Mackenna T. I want to thank you all for coming today, and this is my presentation on predicting the suitability of algae species in Hawaii in future climates using species distribution modeling. First and foremost, I want to say thank you to Papa Jack for endowing the research program. He really impacted my life because I not only did research this past summer, but also last summer as well, and he helped me find my passion for research and science. So I want to start off by talking about algae's role in the marine ecosystem. It performs photosynthesis, so it's very important because it removes carbon dioxide from the atmosphere, which is important for mediating climate change. It also produces oxygen in that process. Algae actually produces 50% of the oxygen in the atmosphere, so if you think about it, every other breath that you take, you can thank algae. However, it can also damage the ecosystem if it grows rapidly, producing blooms. And on the top, that big red C is from a harmful algal bloom formed by microalgae, and it damages water resources and spreads pathogens. On the bottom is a harmful macroalgal bloom from macroalgae, and it's infamous for smothering coral reef and reducing biodiversity. So one of the species that I chose to model was Ulva lactuca, also known as broadleaf sea lettuce. It is a native Hawaiian green macroalgae which serves as a food source for many people and animals. And because it's a native Hawaiian species, it's very important for biodiversity. The other type of algae that I decided to model is Hypnea musciformis, or hookweed. It is a red algae, which is one of the most invasive algae in Hawaii, very famous for coral reef smothering, as you can see on the right. So the purpose of my research was to use species distribution modeling to research how these species will adapt to future climates in order to understand how the balance of native and invasive species will change, and the balance of coral reef and algae populations will change. This will give scientists an indication of what preemptive action needs to be taken in order to maintain the healthy coral reef to algae population ratio. So to start, I collected observation data by going out into the field and just jotting down the coordinates of where the species were. And I also downloaded observation data from the iNaturalist database. iNaturalist is a network that allows anyone to record species sightings in the field. Next, to create a species distribution model, I had to perform a literary analysis to find the species' environmental variable. For both species, this environmental variable was temperature. Hookweed actually tends to grow in higher temperatures from 20 to 25 degrees Celsius, and broadleaf sea lettuce grows at moderate temperatures from 12 to 18 degrees Celsius. Next, I downloaded this environmental variable data from BioOracle, which is a website for marine data layers, and then I used that environmental data to create a raster file in RStudio. Lastly, I ran the raster layer and the observation data through Maxent, which is a software that produced the images with the predictions of the suitability or the species distribution models. So I created 3 sets of these species distribution models, one for the present and then 2 for the future, one in the years 2040 to 2050, which I call the near future, and then one for the far future, which is in the years 2090 to 2100. In each of the future species distribution models, I created 2 possibilities for climates, the best case scenario and the worst case scenario. The best case scenario was representative concentration pathway 2.6, and this is a lot different from representative concentration pathway 8.5, which is the worst case scenario. These RCPs were created by the Intergovernmental Panel for Climate Change in 2014, and they are based off of how we are responding to climate change with climate change policy and strategies. So for the 2.6 RCP, we would be fighting climate change by switching to renewable energy, capturing emissions, and relying on public transport, which keeps the net increase in the atmospheric temperature at 1 degree Celsius. But on the other hand, in RCP 8.5, which is the path that we are currently on, is that we just mainly rely on coal-fired power or fossil fuels, and we allow the atmospheric temperature to increase by 3.7 degrees Celsius. So this was my present species distribution model of the broadleaf sea lettuce, which shows high suitability in Hawaii with that dark orange color. The suitability ranges from 0 to 1, 0 being the least likely and 1 being the most likely. The near future suitability of broadleaf sea lettuce slightly decreases. The area of that dark orange color around Hawaii slightly narrows, and actually, the yellow around it also narrows as well. And then for the far future suitability of broadleaf sea lettuce, it actually shifts upwards, which is in line with climate change predictions, and then also narrows as well. And then this is my species distribution model for the present day for hookweed, and it is very different from Ovalactuca because this is an invasive species rather than a native one. It shows moderate suitability with that yellowish green color in Hawaii. In the near future, suitability of hookweed slightly increases. It goes from that really green yellow to a more yellow color in both RCP 2.6 and RCP 8.5. And then the far future suitability of hookweed also increases, but a more notable part of this species distribution model is that the area of the western Pacific Ocean actually becomes really dark orange color, which is concerning, and the areas around Hawaii raise to a 0.77 probability of suitability. So in conclusion, suitability for Ovalactuca will likely decrease in the Pacific Ocean, while suitability for Hypnea musciformis will likely increase in the Pacific Ocean in both the best case and worst case scenarios. So on the left is a picture of broadleaf sea lettuce, and then on the right is Hypnea musciformis. So the limitations of my research include the fact that my study was only based off of one variable, which was temperature. I wanted to test salinity, but the salinity environmental data was not working with my species distribution models, mainly because of the fact that a lot of my points lied on coastlines, but the salinity data was mainly from the water, so that was a big problem. And then also, my species distribution models is not reliable for any other regions outside the Pacific Ocean, and this is because all of my observation data is from Hawaii. And then some of the implications of my research include helping scientists and local organizations plan for algae conservation and management. So from my research, we can deduct that we need to focus on preserving the native species like Ovalactuca, and then we need to focus on removing and managing invasive species like Hypnea musciformis. So on the left is a Ovalactuca plant here in Hawaii on the Big Island, and then on the on the right is a picture from Malama Mauna Lua, which focuses on removing invasive species in Hawaii Kai. So my research project was full of learning curves. As Dr. Chan mentioned, I had never coded before, so it was definitely a difficult process. There were a lot of obstacles, but in the end, it resulted in a lot of triumphs, and I learned a lot, so I'm very glad that I toughed it out. Some advice that I offer to future K Fellows and current research students is to not be afraid of trying new things. That's what research is for, and don't be afraid to ask for help because you are going to run into obstacles. Lastly, I would like to say that you should all pick something to research that you are excited about and that you love. Otherwise, it gets a little tedious. But yeah. So to end, I want to say a big thank you to Dr. Chan, Ms. Kobayashi, and Mr. Hill. All of these teachers helped me with my research project and helped me learn to code. I also want to give a big thank you to my family and friends who helped me through this process by just being there for me and offering me a bunch of support. These are my works cited, and thank you all for coming.